Very good afternoon and warm welcome to Parallel Technical Session 13. Welcome to the chairman of the session, Professor D.K. Baidya, and co-chair, Dr. Asha M. Nair. And welcome to the SOAP lecture speaker and to all the technical paper presenters. Before I hand over the session to the chairs, for the information of the delegates who are there in the 3D platform, let me share the platform and explain how you can post your questions. And also our guests can see the platform here. So I hope my screen is visible. So this is the platform that we have, the virtual platform where the delegates will be attending from there, where the speakers are actually in the Zoom platform. So our session is in Hall A, the current session. So once you play here, it is live actually. You can watch what is happening in the Hall A. So this is, there will be some 10 seconds lag is there. Anyway, I will close there, otherwise there will be echo. So to post any question, you can see a tab actually on top left, adjacent to the lobby. You can click Q&A and you can type your question there. So the delegates can type your question here in the Q&A, which is adjacent to the lobby on top left. So that the chairs will get it here and the speakers will be answering. So I just wanted to share this information so that delegates do not get confused where to ask question. Well, it is my pleasure to introduce the chair and co-chair of the session. The chairman, Professor D.K. Baidya, is a professor at I.I.T. Kharagpur, and he obtained his PhD from Indian Institute of Science, Bengaluru. He has over 27 years of experience in teaching and research and published over 125 papers in several national and international journals, as well as in the conferences. He provided consultancy services to various industrial problems from National Highway Authority of India, Kolkata Port, Public Works Department, Tata Mines, Indian Railways, etc. Professor Baidya also held several administrative positions at IIT Kharagpur, including chairman as well as vice chairman of the JE for IIT Kharagpur zone for 1 year each. And he has also visited several countries abroad for presenting papers and delivering invited talks. And also he served as a faculty member in the University of West Indies for 2 years.
Thank you.
Dr. Asha M. Nair, co-chair of the session, is a professor in civil engineering at Department of Civil Engineering in the CMR Institute of Technology, Bangalore. She obtained his PhD from I.I.Sc Bangalore in 2011. Her areas of research includes use of waste materials in construction, use of geosynthetics in low volume roads, and fatigue behavior of concrete and asphalt. She published more than 30 research papers in reputed international journals and conferences. Welcome, madam.
Thank you.
Thank you. Thank you.
Now I hand over the session to the chair and co-chair.
So I once again welcome you all this particular session. And it is my pleasure to introduce the speaker, the special lecture by Professor Gabriel. Is a senior lecturer in geotechnical engineering at the University of Canterbury. And his research focuses mainly in earthquake engineering and related problems. And he received his PhD degree in geotechnical engineering at University of Tokyo, Japan. And Dr. Gabriel has authored over 100 scientific publications, mostly in geotechnical earthquake engineering. And he has awarded the prestigious Japanese fellowship in 2014. Also, Gabriel was the team leader of the 2016 NJSEE Learning from Earthquake in Kumamoto, Japan, and team co-leader of the 2015 JGS and JSC in Earthquake Mission in Gorkha, Nepal. So with this brief introduction, I welcome Professor Gabriel for give his lecture. Thank you.
Thank you very much, Professor, for the kind introduction. I will share my screen, and I hope you can see. Can you see my screen?
Yeah, it's coming.
Okay, perfect. It is my great pleasure to deliver these State of the Art and Practice lectures, and I would like to thank you, the organizing committee, for giving me this great opportunity. I just realized my bio was a bit old since we have COVID. In the meantime, I was promoted associate professor at the University of Canterbury. The topic I'm going to cover today is the cyclic resistance and large deformation characteristic of sand under sloping ground conditions, and I will provide some insight using a state-of-the-art apparatus, which is the torsional shear apparatus, which is capable to achieve extremely large deformation. This is the outline of my presentation. I will start with provide some background information and then going through the key objective of the research that I'm going to summarize today. Is a research that started more or less 10 years ago and in collaboration with the University of Tokyo. Then I will talk in particular about the testing apparatus, and then I will show what is the testing material and briefly talk about the procedures. And then I will really focus on the test results, and I will talk about the failure modes that were observed in the laboratory. And then I will move on the cycle resistance of sandy soils, looking from a small strains up to extremely large strains, and I will provide some new insight in that particular regard toward the large strains. Then I will talk about the strain equalizations that can be observed in the laboratory in liquefied soils, and I will show how the results that were obtained using this novel apparatus can be actually used to predict or to back calculate what is the failure of slopes that was observed during past earthquake in the field. And then I will conclude my presentation with some very brief concluding remarks. So let's start with some background. So the photo shown here shows the failure of a slope occurred in 1964 in Japan following a Niigata earthquake. It was a really moderate slope, a gentle slope. The inclination is only 2% or even less. But as you can see from the photos, the damage to building infrastructures and roads and lifeline facilities was quite severe. So it's only 2% slope gradients, but it's a slope made of clean sand, dune sand, which was very close to the river. In fact, the slope to move toward the river for about 8 meters. And therefore, the photos and the damage associated with the liquefaction are shown in this historical photos. So the deformation at 8 meters, and if you consider the average thickness of the liquefied layer is 4 meters, means that basically the deformation on site were on the order of 200%, extremely large shear deformations. So this is an historical case, but also there are more recent cases. For example, in 2015, these two photos here, A1 and 2, shows the liquefaction of non-plastic silty soil, finds only more or less 90% of silt. But you can see the evidence of liquefaction here, the typical sand boils and some fissures in here. But the liquefaction occurred in a gentle slope. Was again, the inclination was 1 or 2% near the Trigely River, and as you can see here, there were large fissures and a lateral spreading for many, many meters, and also going backward from the river about 50 or 100 meters. The other case I'm showing here, it's the failure of a slope occurred in Japan due to the Kumamoto earthquake. In this particular case, is a volcanic soil, it's pumice soil, weather pumice soils, which was sandwiched between impermeable layers of clay. And I will come back to this particular slope later on with more information. But the peculiarity is that the slope again was only 6% in terms of inclination, but the soil covered a distance of 600 meters from the source to the deposition area, and on the way impacted against a new residential complex, destroying 7 houses and killing 5 people. So I show some historical cases, more recent cases, but the key issue is that when it comes to liquefaction of sands in slope grounds, still we have a lot of uncertainties, and we have the design or our capability to predict liquefaction is still largely unknown. And the reason is that the phenomenon is quite complex, and also the way or our capability to test this material in the laboratory is still challenging. So one of the key aspects is that if you look at the stress condition of slope ground before the earthquakes, we already have a component or initial static shear due to the gravitational effect, in addition, of course, to the vertical horizontal stresses. When it comes then an earthquake, we have an additional component, which is the cyclic stress ratio, stress that is in addition to the initial static shear. And the sum of these two components, starting and cyclic stress ratio, give us two stresses. The one that I call maximum shear stresses, when the cyclic shear stress and the cyclic shear stress act downward in the same direction, and one is the minimum, when the static and the cyclic shear stress act in the opposite directions. Of course, the combination of the tau max and tau minimum provides us information how the soils really experience the cyclic loading. In some cases, the combination of these two loads give us the classic stress reversal, where the loads change from a positive value, a maximum positive value, to a minimum positive value. And I will show you that this is the key factor for liquefaction. But if the slope is quite, the inclination slope is quite more than 6 on 10%, and it means the static shear is quite high, very often we don't have the reversal stresses. And this will be another key factor I will show later, that might not trigger liquefaction, but still might be detrimental and might trigger the shear failure of soil. So the initial static shear has been recognized one of the key aspects in regards to the liquefaction in sloping ground, and to evaluate also the effect of liquefaction. Yet, if you look at some of the early studies, starting in 1967, just after the 1964 negative earthquakes, at the same time there was another earthquake in Alaska at the same time, many studies have been done using structural apparatus, but also try to mimic the simple shear conditions, which are more realistic of the stress condition in the field. But if you look at some of the results, the conclusion of some of the preliminary studies, we can see that the effect of static shear is not yet clear. Some tests shows the liquefaction resistance increases with initial static shear. Some other tests show that it decreases with initial static shear. It's not only when we have different testing devices, but even within using the same testing apparatus for some structural apparatus or simple shear conditions, still there is not it's not very clear what is the effect of initial static shear. If we have a very close look, then we realize that some of the inconsistency might be because maybe the relative density of the soils tested were different, or the criteria to define liquefaction was different, or the level of deformations that were used to define liquefaction, or the strength of the soil were different. So I will try to use some of these parameters to clarify what is really the effect of initial static shear. The other aspect is that if you look at the level of deformation we can achieve in the laboratory using conventional apparatus, we are on the order 20-25%. But as I showed before, in the field, we have more than 20-25%. So we need to really have something, new capabilities in laboratory that can help us to study the larger deformations and understand when liquefaction occurs in the post-liquefaction stage. Can we expect larger deformation, or can we predict based on laboratory tests and all the tools that we have? In these two pictures here, the figures in here, I should compare what is the strength of soil in sloping ground using simple shear conditions, so in this case, and triaxial apparatus. So we have two clean sands and tested with similar densities, and you can see that in the case of simple shear, it looks like the initial static shear has a detrimental effect for mostly from loose to medium dense sand, but doesn't have a major effect. Actually, it's beneficial in the case of dense soil. Now, if you look at the other case, the triaxial test apparatus, tests, we can see that in most of the case, it really doesn't matter which density range we look, maybe from 10% to 50%, 70%. It looks like that initial static shear has always a beneficial effect. And the reason because the triaxial apparatus might introduce a certain anisotropy in terms of deformations. We know that in the triaxial apparatus, the deformation tends to accumulate in the extension side of the soil behavior. But the question is that is the triaxial apparatus the best apparatus to reproduce the stress condition in the field? So what we evaluate in the laboratory, yes, is the true behavior of the soils under triaxial conditions, but they are not really representative of the field conditions. On the other side, the simple shear apparatus help us or provide us an opportunity to really closely replicate the simple shear conditions. In order to clarify some of the aspects regards to the effect of static shear on the liquefaction behavior of soil and sloping ground, and also with the intention to be able to evaluate the large behavior of soils, we use a special apparatus. So we try to simulate the larger strain behavior of liquefiable sand sloping ground. That was the key objective. But also we try to identify what are the potential failure modes of the soils, depending on the combination of cycling and cycling, static and cyclic restorations. Then we define the liquefaction resistance from small to large strain levels. And also we assess what was the strain localization in liquefied sands. To do so, of course, we try to simulate as much as possible in a realistic way the behavior of soil. And in this particular study, we use a different combination of static shear stress, cyclic shear stress, and soil density. And because the tests I'm going to show are quite time-consuming, each test takes at least 1 week, and on average, only one test every month is successful. There is a lot of things that can go wrong in these tests. In this particular presentation, I'm not going to touch the confining pressure effect. Okay, so I'll only focus on the first three key factors. Moving on the testing apparatus. So the apparatus we use in the study is a large strain torsion shear apparatus. So this is not a commercial apparatus, is a unique apparatus built at University of Tokyo, with very unique capabilities. We test a hollow cylinder apparatus. So in this particular case, we could control for a degree of freedom, so the vertical stress, the horizontal stress, but the torsion shear stress, but also in terms of vertical horizontal stress, you can control both the outer and inner pressure acting on the specimen. So this is a photo of how looks the apparatus. It's quite large apparatus, has a special loading systems with a gear that allows to apply strain control or strain rate control tests. So you can even evaluate the post-peak behavior in monotonic tests or even in cyclic tests. And also allows to achieve in terms of double amplitude, more than 100%. Okay, so really pushing the boundaries and exceeding large deformations. The other thing it's capable to do is apply the quasi-simple shear conditions by mechanically locking the height of the specimen. So the vertical deformation are 0, and you can apply directly the shear rotating top cap. And the only thing, the other things is to have the simple shear conditions. You have to assume that the radial and circumferential deformation might occur, but they will self-balance each other. So we call these quasi-simple shear conditions. This is a photo of typical specimen large deformations. The specimen we could test has an outer diameter 150 millimeters, the inner diameter 90 millimeters, and the height is 30 millimeters. So extremely large specimens. The material tested by this particular presentation is Toyota sand, which is a clean quartz-rich sand, heavily studied in Japan, so we know all the informations, and we can easily compare our results with past studies and also triaxial apparatus and all the sort of studies. So we have done a large number of tests. So the tests I summarize in the paper are only 26, but in the meantime, I had a PhD student finishing, and therefore we have more test results. And then the yellow table here, I will use some of the additional test results on relatively dense sand. So we have, I will talk about the behavior of relatively loose sand, medium sand, around 40% relative density, but also I will use data for dense sand with relative density about 70–75%. So now moving on the test results. So before starting, I will use this table here. So the idea is that the initial static shears is a key component on the liquefaction behavior of sand and sloping ground. But also we know that the combination of the static shear and cyclic shear might have a key effect, because you might have if the cyclic stress ratio is greater than static shear, the soil will experience the so-called reversal stress conditions. But if the static shear is larger than cyclic shear, then we expect the stress will be always positive and the non-reversal stress condition will apply. On the other hand, also I mentioned that the maximum shear stress is an important parameter, so which is the combination, the sum of the static and cyclic stress ratios. But also, as I will show later on, the comparison of the maximum shear stress we apply during the tests compared with the strength of the soil, this tau peak, will have an influence. So if you put together all of this combination of stresses, we might expect 4 different behavioral zones in terms of liquefaction, non-liquefaction, also a safe zone. So I will use this table here to explain what are the mechanisms from now ahead. So before that, I want to clarify what is this tau peak, or also known as a tau and drain. Basically, if you perform a monitoring test, you might reach a transient peak behavior here, and this peak will be the initiation of instability in sandy soils and in terms and relatively loose soils. After this peak, might experience the so-called static liquefaction. If the soil is not medium dense, you might have a limited flow, and then when reach the phase transformation line, the soil will recover certain strengths and will follow the failure line. So I will use the concept of tau peak to explain why we can expect certain behavior in soil with the initial static shear or not. In terms of tau peak, this undrained shear strength of the soils depends on many factors. Depends on the initial static shear, depends on the density of the soil, and because of that, might be easily estimated based on laboratory tests. So there are equations available like the one I'm showing here. So the first failure mechanism I want to talk about is the one I call potential large shear deformation under cyclic loading. And I'm going to use the case of loose sand, medium dense sand, and dense sand. So in this particular case, if you look at the bottom figures, the soil experiences many cycles of loading, during which the effective stress decreases because there is a generation of excess porous pressure. But before the soils might experience large deformations, the soil has to develop very large excess over the pressure generation, even in the case of loose soils. So in this process, for example, from this point to this point, even though the soils goes many cycles, if you look at the deformations are very, very small. And only when the liquefaction occurs at this point here, then larger deformation and flow failure might occur. This is the case of dense soil, medium dense soil. And in this case, for example, the number of cycles to reach liquefaction 38, and after that, actually the soil still can experience large deformations. In the case of dense soils, actually the soils will not experience large deformation, even though undergoes many cycle loading cycles. So in the end, in this particular case, the soil could experience large deformations, but the question is that how many cycles we need to, or an earthquake we have, and to induce this kind of failure. So potentially, yes, the soil could undergo liquefaction and develop large deformation, but the reality is only if an earthquake is strong enough. In this second case, and I'll go back quickly. In this particular case, the behavior is because the maximum shear stress we apply in the soil does not exceed what is the peak strength of the soil. In this second case, it's clear that the maximum shear stress of the soil exceeded the peak strength of the soils. In this particular case, the soils might easily reach liquefaction, and once reach liquefaction, the soil will experience large deformation. So compared to the case before, rapid or flow liquefaction occurs within a few loading cycles, and therefore large deformation might be expected, even in the range of 50% or more. In the third case, the soils does not show liquefaction. This is the non-reversal case, but at large deformation, the soil will experience shear failure. So a completely different failure mechanism. And this is because of the maximum shear stress of the soil will exceed the strength of the soil, this point here. But if you perform a similar test and now the maximum shear stress will not exceed the strength of the soils, then the soil will not develop large deformations, even though you apply 100 loading cycles. So these are the four failure mechanisms you can expect, considering the combination of the initial static shear, cyclic shear, and also looking at the strength of the soil. And this is a summary of the typical resistance of the soil in terms of alpha, the static stress ratio with number of cycles. And for 3%, 75%, and 20%. You can see that usually loose sand will, as you increase the initial static shear, the tendency of the soil to experience large deformations decreases. So it means that the initial static shear has a detrimental effect on the deformation of the soil. For medium dense sand and large deformations, it seems that at certain points there is a change in behavior where the soil starts to gain certain strength. And this was not observed for small deformations. If you look now at much larger cyclic stress ratios applied, and then we look at medium dense sand, in this particular case, the change from detrimental to beneficial occurs when we have the change between non-reversal and reversal stress. It means that when the initial static shear becomes smaller than the static shear. For dense sand, it looks like that the effect of initial static shear is not as severe as in the case of loose sand. And this is another figures maybe that can help to explain the behavior. So in here we have the cycle stress ratio evaluated at 10 cycles, 3%, 7.5%, and 20%. So we have loose sand, medium dense sand, and dense sand. Again, we have similar results, similar tendency. So as we increase initial static shear, the cycle resistance of the soil decreases for relatively loose and medium dense sand, but quickly recovers for dense sand. And in the case of 20%, 20% was not achieved in the laboratory for dense soil. It's a very strong soils, but was achieved for loose sand and medium dense sand. And can be seen as that in general, the resistance of the soil decreases until reaching the reversal line, and then there is a change, and then the soil starts to recover the strength. You can plot the same results in terms of K alpha, which is better parameters maybe, and you obtain similar results. And in this particular case, it seems that, for example, the K alpha, 7.5%, it's very similar for the three independently from the density, but the way the soil recovered the strength, it then depends on the density. In the case of dense soils, the recovery and the beneficial effect of initial static shears are visible much earlier stage than comparing with the other, the medium dense and loose soil. This is a quick comparison between the tests performed in this study with other relevant tests done found in the literature. So I'm referring here to the black line here, the 7.5%. So these are dense loose sand. The test results in here are similar trends to what was observed in simple shear tests in the case of medium dense, and also in the case of loose sand and medium dense sand. When we compare with the triaxial tests, the trend is quite different. As I mentioned before, is because the conditions or the model deformation of the same soil in triaxial parts, the simple shear conditions are quite different, and we have to be careful how we evaluate the strength of the soils, and how then we use the results. So what we notice in the laboratory that yes, we can achieve larger deformations, but at certain points the deformation are not uniform, no longer uniform in a specimen. You can see, for example, the larger deformations, the bottom part of the specimen is relatively uniform, but the top part of the specimen has much larger deformations. So we are able to identify where is this change in behavior from a uniform deformation to a non-uniform deformations, because that is the limit of deformation you can use from laboratory tests to estimate the strength of the soil. And this kind of approach has never has done properly in triaxial tests, and it's very difficult to evaluate in simple shear devices where you cannot see the specimen. But to give you an idea, for example, you can evaluate what is the difference between the vertical stress and the radial stress if you lock the deformation specimen, and you can identify this point A and point B, and this will give you a clear understanding how is the change in deformations. So you can do this exercise for many specimens, different densities and different other parameters, and you obtains a curve that summarize that helps summarize what is the limit shear strain to achieve shear band formation even in liquid fibrous soils. And it is clear that the density is one of the key factors. Looser soils tend to have strain localization much larger strains, while dense soils tend to have shear bands much lower deformations. But the strain localization depends also on other factors, depends on initial static shear, depends on confining pressures. So actually, we identify other parameters, which is drain shear strength of the soils, that can capture a better way what is a leading shear strain, because incorporate the density, the confining pressure, and initial static shear. To conclude, we have used this method to evaluate what was the behavioral or back calculate or the behavior of slopes observed during or the failure of slopes observed during past earthquakes. This again is the Kumamoto earthquakes, the Takanoa landslide, 6% degree of inclination. This is how it looks like the slope. So the source areas in here, and what I'm showing here, the cross section here are the longest length length in here, and the soil is moved from here to here about 600 meters. We did some limit equilibrium analysis, and the factor of safety before the earthquakes was 3.1. We also did some seismic limit equilibrium analysis, and we found that the factor of safety dropped to 0.8 during the earthquakes, but it did not provide us information about liquefaction behavior. So then we did some laboratory tests. We recover samples of these poems in here. We did some laboratory tests. We compare with the Toyota ascent, and we found that these poems soil behavior could be similar to a medium depth ascent. Then we evaluated what is the K alpha, and we use a very simple model, predictive models, where we can see that if you consider the strongest earthquake of the common mode earthquake, this model might predict liquefaction. What if you consider the foreshock, which was much less stronger, liquefaction not occur, and this matches the reality. Another case is the Niigata earthquake. We had NSPT values and observation in the field for this particular slope. There was a liquefiable soil layer quite shallow, that liquefied, and then again we use this simple method, and this is the CSR line, and our observations, liquefaction zones and no liquefaction zone, match with observation from Armada in Toll 1994. So my time is finished. We'll go quickly through the conclusions. So the evaluation of the effect initial shear on the liquefaction resistance of sandy soils is significantly affected by the testing conditions, simple shear or traction shear, and we should be very careful how to investigate and use the data. The stress reversal plays a key role on the failure mode of the sand, and liquefaction can only occur under stress reverse conditions, while under non-reverse stress conditions, the liquefaction will not occur, but shear failure might occur. There are different failure mechanisms, from potential development of large deformations to flow failure to shear failure, and the most detrimental is the flow liquefaction because it happens without any warning signal. The cyclic strength of the soils, it seems that to decrease, irrespective of the density, to decrease with initial static shear, and therefore, and only under non-reversal stress conditions, then we have the beneficial effect of the initial static shear, which is in opposition of what we found at the actual tests. We noticed that when you reach large deformations in any test you conduct, the soil, even liquefiable soils, might undergo strain localizations, and therefore it's very important to understand when the strain localization occurs, because that might affect the results we have and the way we evaluate the strength of the soil. Before I conclude, I would like really thank you, the key collaborators from the University of Tokyo, Professor Junichi Koseki, my former PhD supervisor, Takashi Kyota, which allows me to use still use this large apparatus nowadays. Takashi Sado, which is developer of the apparatus, and Muhammad Umar, that was my former master and PhD student that has done most of the tests I showed today. Thank you very much for your kind attention.
Okay, thank you for the very interesting lecture. And now, actually, I think we can open for question. I am not seeing the tab for question answers.
I think there are no questions as such, sir. I think
Okay.
question answer session it is.
If it comes, then only it will be there.
Yes, yes. Am I right, Professor Srival, sir?
Yeah. There is no question yet. Yeah.
Okay. So Should we go to the next speaker then, or wait some time?
I think next is paper presentations, I think.
Paper presentation, yeah.
Yes. Oh.
So, question answering will be anytime throughout the session?
Well, as and when it is getting posted, I think it will be getting reflected here.
Okay, then thank you. Then you please take over and invite the other speakers,
Yes, sir. Yes,
presenters.
sir.
Okay.
Yes, sir.
Thank you, Professor Dr. Gabriel.
No problem.
We'll have any question. We'll come back to you.
Okay.
Thank you, Chair, Professor Bhatia, and also thank you, Professor Gabriel, for the wonderful lecture. And in fact, let us try to start with the paper presentations for this TARL Technical Session 13. And we do have 5 paper presentations. Like the paper IDs are 823, 827, 911, 934, and 885. So let us go in the same order. And so, in fact, we will be giving 8 minutes for the paper presentations, and we'll be having 2 minutes for the question answer session. And I request the speakers to adhere to the timings. And so, let me call upon the first speaker. The first paper is the ID is 823. And the topic is effect of metric suction and CSR on dynamic response of expansive soils by Naman Kadeshia, IIT Gandhinagar. Request Kandeshia for presenting.
Sure. Ma'am, is my screen visible?
Yes, yes, please. Please
Okay.
go.
Yes. So, good afternoon, everyone. I'm Naman Kantisaria, PhD candidate from IIT Gandhinagar. My presentation topic is effect of metric suction and CSR on dynamic response of expansive soil. So this is the motivation behind my present research work, as we know that India and in the world, several regions falls under the category of arid and semi-arid regions. In these regions, the majority of the soil remain unsaturated throughout the major part of throughout the year. So this unsaturated zone has a three-phase system which contains soil, solid, water, and air. And due to this three-phase system, it has certain negative pore water pressure, or we can say the soil suction in it. And due to this presence of soil suction, and due to the presence of this soil suction, the unsaturated soil behavior cannot be evaluated through the classical principles of saturated soil mechanics, and we need to include the effect of the suction onto the static and cyclic response of these unsaturated soils. Now, in the past, few researchers tried to study the effect of the suction onto the cyclic response of cohesionless to low plasticity cohesive soils. And actually, the soils have a very low suction range. So they studied for this low suction range cyclic behavior. However, many times geotechnical engineers often come across with the high plasticity expansive soils during the construction of water barrier pores of earthen dams, levees, compacted clay liners, canals, and etc. And as one can see that the suction characteristics of this soils are the suction range for this soils are ranged from the 0 to 10 lakh kPa. So it's a very vast range, and we need to consider that effect of suction and various loading condition to evaluate the dynamic response of such expansive soils. So this is the objective of the present research. The soil for the present research was collected from the left bank canal of Gosikut Dam, Nagpur, India. This soil contains around 60% clay-sized particles and the plasticity index of 48.5%. And the soil, based on that, they classified as CH type according to Indian Standard Soil Classification System. And it has a DFSI value of 123%, which indicates this high degree of expansiveness. The experimental program is divided into the two portions. The first portion, in which the suction characteristics was evaluated through the filter paper test. All the filter paper experiments was conducted for the degree of saturation range from 30 to 95%. This is the pictorial representation of the procedure to do the filter paper test. All of these tests were conducted at a dry density, at a constant dry density of 1.34 gram per centimeter cube, which is roughly around 96% of MDT. And based on the result of this filter paper test, the stress control cyclic simple shear test were conducted at 4 chosen degree of saturation: 30%, 50%, 70, and 95%. And all of at this degree of saturation, the CSS test was conducted at a CSR of 0.1, 0.3, and 0.5. All of these tests were continued till 1000 number of loading cycles. So this is the results of the filter paper test. As one can see that this SWCC we can present from the Nagpur soil. This gives the relation between the degree of saturation and the metric suction, and to evaluate the response of metric suction into the full range, the mathematical fit provided by Fredland and Zing was used. And as per the recommendation of Professor Vanapalli, this SWCC has been divided into the 3 zones, that is boundary effect zone, transition zone, and residual zone. And to further continue my experiments for the cyclic simple shear and to represent each of this zone, the degree of saturation that represents each of this zone, that is 95%, 70%, 50%, and 30% was chosen. So this is the result of the cyclic simple shear test. As we can see that for the case of CSR is equal to 0.1, the inclination angle of the hysteresis loop or cyclic stiffness of the system was increased as the degree of saturation of soil reduced from 95 to 30%. However, this was not the case for CSR of 0.3 and 0.5. In this case, the inclination angle of the hysteresis loop was found to increase with the decrease in degree of saturation from 95 to 50%, and with further reduction in degree of saturation to 30%, the inclination angle again reduced. It means that the cyclic stiffness again reduced. Now, this is the similar case for CSR 0.3 and 0.5. This is the cumulative cyclic strain response. When the cyclic strain obtained was plotted with respect to number of loading cycle, as one can see that for the case of CSR 0.1, almost same cyclic strain generated throughout the 1000 number of loading cycle. Whereas for the case of 0.3 and 0.5, the amount of cyclic strain generated was increasing with the rate and amount was increased with increasing number of loading cycles. This indicates that for the case of CSR 0.1, the amount of generated total strain remain majorly elastic in nature, and based on that we can conclude that for this particular case the threshold loading amplitude was CSR is equal to 0.1. Now when the maximum cyclic strain that is generated during each of these 10,000 cycle was plotted with respect to metric suction, it was found that the CSR the cyclic strain amplitude was found to reduce with the increase in metric suction till the metric suction corresponding to 50% degree of saturation. And after, with further increase in metric suction or reduction in degree of saturation, the cyclic strain amplitude was found to increase. This was case for the CSR 0.3 and 0.5. And as to see the effect of CSR, as it's obvious that as the CSR increases, the amount of cyclic strain generated was increased for all the metric suction range. Now to evaluate the dynamic parameter, cyclic stiffness, the shear modulus was evaluated for each number of loading cycle, and it was plotted with respect to number of loading cycle. So as previously concluded for the case of CSR 0.1, it remained almost same throughout the cycle, that further strengthened the our conclusion that the threshold loading amplitude for this particular cycle is 0.1. And as the CSR increased to 0.3 to 0.5, the G was found to reduce with the number of loading cycles. And when the first cycle G was plotted with respect to metric suction, we can see the significant increase in the cyclic stiffness with increase in metric suction till 50% SR. And after that, again, it started to reduce. Now, based on this observation and the previous observation, we can see that the SR is equal to 55 can be considered as our critical degree of saturation, after which the behavior of the soil changes. Now, again, to see as the effect of CSR on the G, as CSR increases, the amount of shear modulus that is generated is decreases for all the metric suction range and throughout the number of loading cycles. The another important dynamic parameters is the damping ratio. Damping ratio represents the ratio of the dissipated strain energy to applied elastic strain energy. And as one can see that damping ratio was evaluated with number of loading cycle, and it was remained fairly constant throughout the cyclic loading for both 0.1, 0.3 and 0.5% CSR. Now, when this first cycle damping ratio was plotted with respect to metric suction, it was found that the damping ratio also shows a similar trend, that it is decreased continuously till SR50, and again it increases. And from this also we can conclude that critical degree of saturation as 50%. Now, with the increase in CSR from 0.1 to 0.5, the damping ratio was found to increase for all the metric suction range. Now, this is the microscopic representation of the critical degree of saturation concept, that why it is happening that till certain degree of saturation it is increases and then decreases. To see that when we added the very low amount of water to the to form the compacted specimen, it forms the aggregate structure. And within this aggregate structure, when we added the water absorbed by the clay particle interlayer spacing, and very less water is available between this intra-aggregate pores. And that's why even though suction is very high, it did not contribute to the shear resistance of the specimen. And with further addition of the water, once this microporosity of the water is satisfied, the water started to appear in the macropores.
Sorry, Kandishriya, your time is up. Like to wind up your slides in another 1 or 2 minutes.
Sure, ma'am. In 30 seconds, I'm winding up. Yes, ma'am. So with increase in the water bridges, the shear resistance of the soil increases, and when all these intra-aggregate pores are connected through the water bridges, the specimen reaches the critical condition and a critical degree of saturation condition. And with further addition of the water content, these bridges are lost, and the suction effect reduces, and the shear resistance of the soil reduces. This is the SEM image of the Nagpur soil, which shows the aggregate structure with the intra-aggregate pores. And when the zoom in was done into the particular aggregate, the clay particle layer structure was observed with the intra-aggregate pores within that. This is the major conclusion from my study that I already explained. However, I want to focus on the two conclusion again, that for my study, I obtained that the threshold limit for the critical threshold loading amplitude was obtained as CSR 0.1, after which if we increase the loading amplitude, the significant cyclic degradation was obtained, and critical degree of saturation was obtained at 50%. So that conclude that not just based on matrix suction value or soil suction value, we conclude the soil behavior. We should see the microstructure formation of the soil as well in terms of micro and macroporosity. So these are the major conclusions. These are the references. Thank you.
Thank you, Kandishriya. So I think Professor Bhatia, like there is a question, I think it is for the session SOAP lecture. So, sir, would you like to, I think for this session as such, I think we don't have any question session answer itself. So Professor Gabriel, actually there is one question from the audience end. Bhatia sir, like shall I read out the question?
Question is there?
Yes, it is there, the question answer session. Question answer tab, yeah. For Kandishriya session, there is no question answer right now.
No, I did not see any question actually.
Yeah, shall I read out the question actually?
Okay.
Professor Gabriel, actually, yeah, the question is like this: how the behavior of sands will differ from that of clay?
Well, clay soils per se do not liquefy. Some of the clay soil might experience larger deformations, but the phenomenon is not linked with liquefactions and more strain softening. And so the study I focused was on clean sands that liquefies, and in particular using a lot of data from loose to medium dense sands. When it comes to clay, usually clay material, the plasticity is very high, so it means that there is a strong bonding between the particles that prevents the formation of the excess poverty pressure. Yet, some of the clay materials, if mixed with sand, for example, might experience a behavior which is might lead to a strain softening during a cycle loading, which might lead to large deformations. But in reality, liquefaction not occur in clay soils. So the behavior of clay soils in slopes is completely different. The case I showed before, where there was clay soils and pumice soils for the Kumamoto earthquakes, the clay soils did not liquefy. It was the pumice soils that liquefy in a similar way that sandy soils might liquefy. There was no time to show all the results, but in terms of poverty pressures, that particular pumice soils actually shows poverty pressure typical of sandy soils. Although because it's a weather material, then there was a little bit strain softening, large deformation, but it's completely different topic, so it was not really relevant for this study. But the clay soils itself, in that particular case, in that particular slope, did not liquefy. But because it was on the top of liquefied soils, then it moved together with the clay soils, and because it was much stiffer, it just broke into pieces, and you can see the blocks of materials. But clay soil per se is much, let's say, stronger material under cyclic conditions as compared to loose sand.
Okay, thank you, Professor Gabriel. Yeah, thank you, Kandeshwaraya, for your presentation. And now I would like to call upon the next speaker. That is, the paper ID is 827, and the topic is seismic stability of non-homogeneous cohesive soil by using calculus of variation. And the speaker is Saurav Sarkar from IIT Varanasi. So over to you, Saurav Sarkar.
Yes, ma'am. Is it visible, ma'am?
Yes,
Yes.
yes.
Yeah. So, good afternoon, everyone. Myself, Saurabh Sarkar. I am a PhD student. I am doing PhD under supervision of Dr. Manas Chakravarti. Today, I am going to present my paper on seismic stability of non-homogeneous cohesive soil by using calculus of variation. My presentation contains calculus of variation, slope stability problem, that means in introduction, problem statement, analytical formulation of the problem, result discussions, comparison of the result, conclusion, and few differences. And first of all, we have to know what is calculus of variation. Calculus of variation is a field of mathematical analysis that uses variation to find maxima and minima of the functional. Functional means function of a function. To extremize the functional, necessary condition is always needed. Thanks to Euler-Lagrange, who introduced the necessary condition. The statement of the Euler-Lagrangian equation, if y is a extremal of I is an integral. Here, f is a functional. Functional, why it is a functional? It is depend upon x, y, and dy dx. Then y must be satisfy the below differential equation. This equation is a necessary condition to extremize the functional. And in introduction part, slope stability problem, as we all know, slope stability analysis is a classical problem in soil mechanics. And it is well known to the fact that the slope stability problem is a indeterminate problem. In order to make this problem determinate, few assumptions is being considered in limit equilibrium method. In variational method, the beauty of the variational method is there is no need to consider any kinematical assumption. That means shape of the critical slip surface or any statical assumptions. That means distribution of the normal stress along the slip surface. Unlike the conventional limit equilibrium method, the factor of safety for any slope is defined as a functional of normal stress and the slip surface. And we previously we said that the functional is minimized using Euler-Lagrange equation. This is a necessary condition to obtain the critical factor of safety. Critical factor of safety means minimum factor of safety we have to obtain. In problem statement part, this figure shows that a rectilinear slope of angle beta with non-homogeneous slope, non-homogeneous undrained cohesive soil. At the top, at the ground surface, Cu naught is the undrained cohesion, and it is linearly increasing along the depth. And the undrained cohesive soil is subjected to vertical and horizontal seismic forces. It is intended to determine the critical failure surface and the critical factor of safety for the given slope. Here the primary unknowns are the failure surface. We don't know the how the shape is the failure surface, and we don't know the entry. This one x naught point is the entry point and x3 is the exit point. We don't know these points. So then we go to analytical formulation of the problem. If we divided the slope into n number of slices, if we consider any ith slice, here the weight Wi is the weight of the soil, and Fb is the vertical seismic force, and Fh is the horizontal seismic force, and delta Li is the length of the soil wedge, and delta Xi is the width of the soil wedge, and alpha I is the inclination angle. If we resolve these forces along horizontal and vertical direction, we get factor of safety is equal to this term. It is a like the conventional limit equilibrium method. It is a top portion, numerator portion is the available resisting forces, and this denominator part is the driving forces. If we substitute this FH and FB value, it is a kV is the vertical coefficient of the seismic forces and horizontal coefficient of the seismic forces. If we plug it into this formula, we get this kind of expression. If delta x, delta width of the slope is width of the slice is very small, we can consider is as an integration summation converted into integration, and it is factor of safety is also a functional because it is function of slope surface. Slope surface means this is a function of Fi is the slope surface function, and Yi is the slip surface function. And next part is to obtain the critical slip surface and corresponding critical factor of safety, we have to use necessary condition, that means which introduced by Euler Lagrange. This equation we have to use. Then we got the final expression of critical factor of safety, this one. Then from the above from this equation, the slip surface can be obtained in 3 different ranges. If we the rectilinear slope can be expressed as mathematically. For this region, we have to divide the slope into 3 regions. For this region up to x1 point, the f1x, the slope surface function is 0, and x1 to x2 point, the slope surface function hx divided by h1, and for x2 to up to the boundary point, it is h. The failure surface pattern which we calculate obtained, it seems to be parabolic. This expression seems to be parabolic. Here bi and di is the integrating factor. The unknowns are, there are total 9 number of unknowns. The bi di, that means the integrating factor is also unknown. There are 3 number of equations is 3, and each equation contains 2 integrating factor, that means 2 into 3 6. Entry and exit point, that means x0 and x3 point is also unknown, and the critical factor of safety is also unknown. That means total 9 number of unknowns is there. So to get unique solution, 9 available equation is needed. So 9 available equations is at the end point we apply 2 transversality condition and 2 boundary condition, and at the intermediate point x1 and x2, 2 continuity condition, 2 natural boundary condition, and the equation for the factor of safety. So total 9 number of available equation is there. So we get unique solution. For this part, for region 1, we got y1 is the equation of the failure surface, and y2 for this region x1 to x2, we got y2 point, y2 failure surface, and y3.
Excuse me, sir. Excuse me, Saurav. Actually, your time is up, so try to quickly finish your presentation.
Okay, ma'am. Result and discussion part is the geometry property is the slope angle. We vary it from 20 degree to 90 degree, and material properties is seismic cohesion coefficient lambda, and the seismic loading we have, and we assume that the slope is fail due to toe failure, and for in result part, for different seismic loading, when the seismicity is increases, the factor of safety as usual it is decreases. When the lambda cohesion coefficient is increases, the factor of safety is increases. When beta is increases, the factor of safety is reduces. This is a graph for same conclusion can be drawn from this graph. And there are some few critical slip surface. When the geometry profile changes, the slip surface is changes. When the seismic forces is increases, the volume of this within this failure surface is increases. That means factor of safety is decreases. In comparison part, we compared with for static case and for pseudostatic case, and the result is quite agreeable with the available solutions. And conclusion part in this study, the major conclusion is that there is no prior assumptions on shape of this failure surface. The factor of safety decreases with increase in KH and KB value and decreases in soil strength. The factor of safety reduces drastically with the increase in slope angle and decreases in cohesion coefficient, that is lambda, for both static and pseudostatic cases. This is few differences. Thank you.
Thank you, Mr. Saurabh.
Okay.
Let me see, like there is one question answer. Yeah, actually this question is also towards Professor Gabriel.
Okay. I think I can answer live. I can put it. Then I think it will go to Candid.
Yes. Yeah. So shall I read out the question, Professor Gabriel?
Okay. I think Dr. Gabriel can see the my screen. No, I think.
No, it is there in the question answer tab. That is there down.
Okay. So I can read also.
Yes, sir.
So the question is to Dr. Gabriel. Dear sir, how will be the behavior of soil if the initial static shear stress applied for dense specimen, say 80% relative density? That is the question. Will the failure be delayed or same as that of lesser dense specimen? This is the question.
Okay, I will try to interpret the question and answer. So the key points that for dense soil, very likely in sloping ground, those soils will liquefy. It's very unlikely, but there is likelihood is that if they are subject to extremely strong earthquakes and the inclination of slope is high enough, the combination of cyclic and static shear stress still might trigger large deformation in the soils. And as I show, in these particular soils, the formation shear bands occurs much early stage. So we don't expect actually to have liquefaction or large deformations. The occurrence of shear band might happen at much early stages. That some of the tests I show refer to 75% relative density. So 80% or 75%, there is no major difference in between the two. The key points that very likely will liquefy, but they might experience shear failure. So if you use it as a liquefaction, the criteria 7.5%, it's not only liquefaction, but will include also cyclic deformation, so that we some failure might occur in those soils. But we need an extremely strong earthquakes, and also the slope might be required to be quite steep.
Thank you.
Yeah, so right now we don't have any other questions for the other speaker. So I would like to call upon the next speaker. So the next paper ID is 911, and the topic is comparison of small strain modulus of beach and volcanic sands. And the presenter is Mr. Shaurya Sood, University of Canterbury, New Zealand. So over to Shaurya Sood.
Is my voice audible to all of you?
Yes.
Thank you. I'll just share my screen. Hello all, I'm Shaurya Sood. I'm a PhD student at University of Canterbury, and I'm working with Dr. Gabriel Chiaro, who is also the keynote speaker here today, with Dr. Thomas Wilson and Dr. Mark Stringer. The title of my presentation is Comparison of Small Strain Modulus, Gmax, of Beach and Volcanic Sands. Talking about the contents of my presentation, I'll be briefly talking about the background and the scope of my project, the materials investigated, and the experimental procedure used, and then finally go on to results and discussion and the concluding and the concluding remarks associated with today's presentation. Talking briefly about the background, the North Island of New Zealand has always been a region of high volcanic activity, especially when we talk about the central North Island, considering townships such as Rotorua and Taupo, which are one of the major volcanic hotspots in the world. Going to the northern part, and when we talk about northern North Island, we can take an example of Auckland City, which though not active as the central North Island, still potentially consists of 53 remnant volcanic sites that have erupted in the past. Now, a common feature pertaining to both of these parts of the North Island is the production of high amount of volcanic products, ash and airfall tephra deposits that result and therefore cause storage problems for the nearby areas, not to mention disrupting the day-to-day functionality of the city. A typical example here shown is a study by Josh Hayes, in which the estimated volcanic products were about 10 to 15 million tons if a volcanic eruption was to happen today at Mount Eden. When we talk about volcanic products, which is briefly the scope of the presentation, and when we talk about a country such as New Zealand, the tectonic location of a country such as New Zealand urges us to understand the soil properties from a seismic point of view as well. Say, for example, when we are talking about inland and when we design to need and when we need to design structures, for example, with urban excavations, then the stiffness in the small straight category plays a very important role, as it enables us to predict ground movements. Therefore, here lies the importance of estimating Gmax accurately. Now, just briefly talking in the last slide, which is also the motivation of the study. When we talk about like 20 to 30 years back, beach sand and gravel were and are the traditionally used products which we use for land filling. But owing to the high cost associated with these kind of products, we have also gone in the favor of using locally available products. Say, for example, volcanic soils such as Masado, which is a decomposed granite, or Shirasu, which is also a decomposed airfall tephra deposit, basically of rhyolitic nature. And talking also about products that are different from natural resources, we can say, for example, coal wash and steel furnace slag, which are byproducts of steel industry, but still have a high potential to be used as refiller materials. So the materials investigated in my study are volcanic and beach sand, the volcanic being the Kaharua ash. The name Kaharua is given to it from the 1305 Tarawera eruption, which was basically rhyolitic in nature. The difference between the two soils is the formation processes associated with volcanic soil that enables that enables the formation of pores within the grains, which makes them lightweight and crushable from engineering point of view. This is briefly the experimental program that I used in the study. So the tests that I carried out were on dry specimens. The specimens roughly measured 61 millimeters in diameter and 130 millimeters in height, with the transmitter bender element placed at the top pedestal. The preparation was carried out by taking the soil in 3 equal layers and horizontally tapping it until the desired densification was achieved. The as the purpose was to see the performance of the soils at relatively higher density, the specimens were prepared in a dense state at a relative density of 70%, and the Bender element tests were carried out at low pressure range of 25, 50, and 92 kPa respectively. Talking about the results, as the airfall tephra deposit, the Kaharoa ash consisted of particles up to 37.5 millimeters. But for this study, the range was cut down from 2 millimeters to 75 microns. So as we can see, both of the soils are fairly uniformly graded or poorly graded materials, with the differences obviously in the specific gravity, the Kaharo ash being volcanic in nature and consisting of voids, which obviously lowers the specific gravity and also higher the void ratio of the same. Now talking about further the experimental results, we tested a broad range of frequencies, right from 5 to 15 kilohertz. And broadly speaking, and before selecting the frequency, we made an estimation of the performance at each frequency. The method used in our study was the first time arrival method to calculate the shear wave velocity. The distance of the wave propagation was taken as the tip to tip distance of the benders, with the vertical motion of the wave permitting the horizontal motion of the particles. Here is the figure shown here is a typical test of the New Brighton sand carried out at 5, 17, 10, and 15 kilohertz. And broadly, there was no difference, of frequency on the arrival time. And a reference frequency of 10 hertz was selected to evaluate the first arrival time of shear waves.
Sorry to interrupt, Shaurya, like, can you just make make it quick?
Yeah, quickly.
Yeah, surely, ma'am. So yeah, just I'll conclude. So yeah, as I said briefly, there was no major effect of frequency on the Gmax. But yeah, with the effect of confining pressure, the shear wave velocity and Gmax for the traditional hard-grained beach sand was higher in comparison to the volcanic sand. This was due to factors such as lower specific gravity and higher void ratio associated with the volcanic sand. And yeah, finally, to inculcate the effect of the particle shape and void ratio, the Gmax was normalized, and yeah, the effect was similar with higher Gmax for NBS in comparison to Kaharu ashes. And yeah, as both the materials differed in terms of gradations as well, the effect of Cu and D50 was taken by considering some past studies. And what was observed that all the previous studies tend to underestimate the Gmax with maximum error going up to 75% for the Kaharu ashes. So yes, this is briefly what I've told ahead as well. And yeah, what further can be done in this is to estimate, is to negate the effect of different gradations for both the soils, and therefore carry out some additional tests in this regard. Thank you so much.
Yeah, thank you, Mr. Shaurya. Like, right now we don't have any questions in the chat box, so let us try to call upon the next speaker. So we have with us the next speaker. The paper ID is 934, and the topic is Need for Artificial Intelligence in Geotechnical Earthquake Engineering. The speaker is Leonardo Sosa and Goa Engineering College. Over to Leonardo Sosa.
Yeah. Thank you very much.
It's not that clear.
I think there is a bit of echo.
Looks like net problem.
Now we have got net problem, sir. Okay, can you hear me?
Yes, yes.
Yes, now.
AI and neutral networks, AI in civil engineering, earthquake engineering, and my conclusion. This is a branch of computer engineering. It's an emerging branch. Sir, can you hear me?
We can hear you, but there is some echo, we feel, actually.
Echo and
To create
There's a break in
computers as intelligent as human beings. Okay, artificial intelligence. Okay, the aim is to create computers think like machines, and this is now not such a new, but it is there everywhere around us. Artificial introduction to AI, AI networks. So AI is a branch of computer science that deals with trying to make computers think and behave like human beings. We use various software together so that the computer thinks for us.
I think it is difficult.
Okay, AI is used in civil engineering to monitor stress and damage, access durability, environment degradation for many such purposes, including concrete mix design, project planning, tidal forecasting, and for earthquake engineering. Mainly it is done for structural engineering, but there is a need to do this also for algorithms, artificial immune systems, neural networks, particle swarm option, and there's theories in which they try to make computer think like a human. Okay, in geotechnical engineering, they much scope predict because there's a great variability over there, and the number of calculations required.
Probably we can come back after the next
After
speaker.
the yeah, you can go for next one.
So Leonardo, we can have your presentation after the next speaker. So the next speaker, like the paper ID is 885, and the topic is linear and nonlinear site response study of soil tire crumb mixture. And the speaker is Mr. Naresh Dikshit from BMS College, Bengaluru. Over to you, Naresh. Mr. Naresh.
Yeah, thank you, ma'am. Good afternoon, chairperson, co-chair, and all the other distinguished speakers. So, I'm Naresh from BMS College of Engineering. So, I'll be presenting on linear and non-linear site response studies of soil tire crumb mixture. So, these are the topics that I'll be covering: introduction, a brief literature survey, gaps, what methodology was employed, results and discussion, conclusions, and future scope. So the basic introduction is, as we all know, like a Oklahoma economist came up with a survey which said that around 48 earthquakes of magnitude 5.5 or more have caused around 232 billion US dollars damage, and almost more than 8,000 people, 800,000 people have died due to earthquakes between 2000 and 2015. And current seismic resistant methods are expensive, and they are not affordable by all. And also, the disposal of tires is a growing environmental issues and concerns. So from morning as well, many speakers have presented various topics of reuse of these tires, which are an environmental hazard. And since tires are made up of rubber, they have an inherent energy absorption and energy absorption capacity, and also damping behavior of rubber is a well-known property. So I intend to use this in soil so that it can be used as a base isolator or earthquake mitigation purpose. It can be used. So that is the basis of my study. So there are many papers into to tell briefly, like they have done lot of research into sand and tire crumb mixtures, and lot of properties like the shear strength, energy absorption capacities, etc., were studied by Dr. Anbalagan and Manohar in their paper. And also there is studies on compressibility behavior of sand tire crumb mixture, which showed that more than 10% growth in brittleness index was shown by Mr. M. Naishek and his colleagues in his paper. And also a paper on site characterization due to site response studies was studied for especially Bangalore area, because my study was focused on for Bangalore area. So from that, it was found that shear wave velocity or PGA was between zero point 0.1 and 0.36 PGA for Bangalore region. And from the literature, it was found that there was a certain gap. Most of the papers were studying on soil as usage of sand with tire crumbs because of coarse properties of sand. But I thought that sand, since it's not universally available and it is costly, to have a low cost affordable thing, why can't use soil which is having more coarser particle? So that was the inspiration behind this research. And further, most of the experiments, since it was covered for sand and tire crumb mixtures, so I did most of these experiments for soil tire crumb mixture, which especially for soils which are having more than 50% of coarse particles, to see if it can be used as a base isolator. And so this is the basic methodology that has been employed. So sampling was done at select locations where borehole data was available, and sieve analysis was done to find out what is the D50 value and to check whether the soil is having more coarse particles or not. Direct shear test and UU triaxial unconfined undrained triaxial test was done as per the IS codal provisions. And finally, linear and non-linear site response studies were performed by using the software Deep Soil. So Deep Soil, it's basically a software which can perform both all the types of site response studies, be it linear, equivalent linear, and even non-linear in frequency, and as well as both time domains. And this is the flow chart of Deep Soil software. We have to select the type of analysis, then if required or not required, depending on our requirement, we can go for pore water pressure generation and bedrock properties and input motion, that, as I said in the beginning, I have selected 0.1 G and 0.36 G based on the literature, and response spectrum and damping ratio needs to be selected and output will be obtained. So this is the GUI of the Deep Soil interface, where we have to select what is the type of analysis that we are going to perform, whether if it is time domain or frequency domain. And also in that, we have to select whether it will be linear or non-linear. Then pore pressure generation, we have to select based on our requirement. And then this is the interface of elastic half space, where this shows a nonlinear study, where all the layers from the borehole data is selected and its thickness have been entered, and the density, shear modulus of the layers and the damping ratios of the layers have been selected. So what we tried here was, based on the laboratory experiments, we tried to replace the soil layer with the soil tire crumb mixture and increase the thickness by 0.25 meter interval. And for each and every sample, we try to study how the PGA or the maximum displacement or the stress has been influenced. So this is one typical output of the analysis that were performed in the Deep Soil software, where PGA, maximum stress ratio, and the maximum shear stress ratio and the stress ratio plots can be seen. So coming to the experimental part, so as I said, we performed all the basic index property studies in the lab. So this is a sieve analysis for the 5 samples that we are presenting here. So the D50 value, CU, CC, as we can see, most of the soil is a poorly graded sand. So most of the sites that we covered were in eastern parts of Bangalore. So most of it was a poorly graded sand, and all of them had more than 50% coarse particles, except site 5. So and coming to the direct shear test, so it conformed to the IS code provisions. And as we can see from the graph, when a normal pressure of 50, 100 and 200 were selected for our test, and the soil tire crumb mixture, the percentage of tire crumbs were varied from 0 to 10 in the intervals of 2.5. So as we can see from the graph, this is for site 1. So as we can observe from the graph, there was a 27.13% increase in the shear strength of the soil at 100 kilopascals normal pressure. So based on this results, we selected that 5% is an optimum percentage for the given site, and similarly for each and every site when it was observed. So there was an increase of 27.13%,
Sorry
22.81%,
to interrupt.
11%.
Sorry to interrupt.
Yeah, ma'am.
Sorry to interrupt. Your time is up, so try to wind up the presentation.
Yeah, in 1 minute I'll be winding it up.
Yes.
So different percentages. Similarly, UU triaxial test also gave a result that almost 43 to 50% increase was there in the strength of the soil. And in the energy absorption, we could see that almost 81% increase in energy absorption capacity of the soil was found out in certain specific sites. And when deep soil, both linear as well as non-linear tests were performed, this table shows all the sites together. There was almost 5 to 10% decrease in PGA of the top layer, so which is significant when compared to earthquake damages. So, and even in non-linear analysis, when it was performed for both 0.36 G and 0.1 G ground acceleration, so a synthetically developed time history, so we could find that almost 15% reduction in PGA for each and every layer. And optimum was when 1.25 meter of soil tire crumb mixture was replaced beneath the foundation level. So overall, we found out that there is an effective increase in shear strength, energy absorption capacity, as well as ductility of the samples. And there was a general reduction in PGF in the range of 10 to 15%. So further, we thought that we should try to study more soil samples in a similar manner, and certain analytical or even experimental methodology, if developed, it can be useful for earthquake damping and mitigation purposes. So these are my references. So thank you.
Thank you, Mr. Naresh. Actually, I think we don't have any other. Yeah, I think Leonardo has not yet joined. So I think we have come to the end of presentation. So
Can I have a quick question? I don't have the possibility to use the question and answer.
Yes,
I'm working on the similar topic. I'm interested at the last presentation if they evaluated the compressibility of this material when they use 10% of rubber or so on.
I didn't get the question, sir. Which property?
Have you, so you evaluated the strength of the materials and the seismic behavior.
Yeah.
But have you evaluated the compressibility in the long term, the creep behavior of this material? Because you are suggesting to use 1.25 meters of this material. So I suggest to you to evaluate carefully the compressibility of this material.
Yeah,
I'm working on a similar topic, and I can share some insight, later on if you contact me.
Yeah, sure, sir. I'll contact you. We are actually planning to study its compressibility behavior now. So in the further studies and increase the number of samples as well. I'll surely contact you and take your help as well. Thank you.
Okay, thank you.
So I don't think we have any other questions. So I think let us, sir, with the permission of yes, sir, can I summarize the session, sir?
Yeah, okay.
Yeah, so we had 5 paper presentations in this session, and out of 5 paper presentations, actually we have got 4 paper presentations being done, and one presenter, he could not present because of the poor connectivity. And the first presentation was from Naman Kandeshriya from IIT Gandhinagar. And in fact, in the presentation, the scope of investigating the microstructure, in fact, in the evaluation of CSR was highlighted. And second, we had presenter was Saurav Sarkar, And in fact, he has used the calculus of variation approach in order to investigate the stability of non-homogeneous cohesive soil. And the third speaker we had was Shaurya Sood. And so Shaurya Sood has tried to use a bent element test in order to evaluate the suitability of organic sands for seismic mitigation. And in fact, we had another interesting actually paper. In fact, it was on artificial intelligence in geotechnical earthquake engineering, which the speaker could not present because of the poor internet connectivity. And we had last speaker was Naresh, Mr. Naresh Dixit. And in fact, Mr. Naresh has highlighted the use of tire crumb mixture, in fact, for mitigating earthquake. So I think with this, we have come to an end of the technical paper presentations in the 13th session. So over to Chair, Professor Bhatia. I would also like to extend my sincere thanks to the ICRAG, the organizers, for giving me this opportunity. Thank you. Thank you.
Thank you, Asha. So now we are almost end of this session, and this session was quite interesting, and all speakers talk about very recent topic. And this is particularly liquefaction is an important problem in geotechnical engineering. And in fact, about 25 years back, we heard this talked about liquefaction in India particularly. And we seriously started liquefaction and actually after Bhuj earthquake, what I remember, because when I was a student, we did not hear much about liquefaction. So perhaps around close to 2000, actually, when the Bhuj earthquake was there, and then everybody started, actually, a lot of phenomena was observed. And then it started liquefaction study in India, actually. And of course, around the globe, good number of people are working on it. And I could see our participants here also, a presenter also, they have taken suitably good topic, including the artificial intelligence. This is also a very essential, actually, this topic, because every field, actually, this artificial intelligence is coming in very big way. And perhaps we also have a very good scope. Though he has introduced some rubber scrap, actually, but even a normal geotechnical application, a lot of scope, I think it will be coming in very soon. And I thank Mr. Dr. Gabriel for a very interesting presentation at the beginning. And also I thank all presenters taking the appropriate time, good topic, and presented here. And finally, whatever we presented here and we have discussed, one or two questions also. And with this, I hope we have learned something a little, and this will be helpful to further our research. And with this, I'll conclude this session and hand over to the organizer. I think Shivalsa, you are here.
Yes, sir. Yes, yes. Thank you, Professor Bhatia and Dr. Asha M. Nair for very efficiently conducting this session. So you have concluded the session on time, and I understand one presenter could not join. Actually, I am also very adjacent to that region. It is very heavy rains. Even I also had lost connection, and here power also went off. So unfortunately, he could not present. Maybe at another occasion, he will be able to present. So once again, my special thanks to both the chair as well as co-chair, and also to the keynote speaker, Dr. Gabriele, and to all the presenters for making this session a grand success. So there were around 88 plus delegates watching this live on the 3D platform, as informed by the platform developer. So it is a very excellent participation, and it was a very interesting session. So thank you, chair, co-chair, speaker, and presenters. Thanks to all the participants. Thank you.
Thank you very much.
Thank you very much.